All right, this is lesson 214, fitting lines to data. In this lesson, we're going to learn how to create an equation for data that seems to follow a linear trend. In other words, lines up. But maybe they don't line up perfectly, but we can still model that with an equation, and we're going to find out what we can do with that equation once we have it. A line of best fit is a line that fits all of the data points as closely as possible. So here's the deal. Students in a science class are measuring how far a cart traveled each time the wheels rotated once. In other words, every time this wheel goes around once, how far did the cart go? So they measured the distance for 1 rotation, 2 rotations, 3 rotations, and so on. The wheels of the cart are 2.5 feet in circumference. And you can see the results on the graph. Now, would you expect the student's data to lie on a line? If so, explain why and give an equation for a line. Now, I'm thinking I would believe that it would lie on a line, and that's because the distance that the wagon travels will go up by a constant rate per revolution. And that constant rate is the circumference of the wheel. In other words, whatever this distance around the wheel is, that's how far that wagon will go each rotation. And since we know that the cart, the wheels are 2.5 feet in circumference, that means there's 2.5 feet around. Each time a wheel goes around once, that cart should move 2.5 feet. So, what I'm thinking is the data should look something like this. If this is the number of rotations, R for rotations, and D for distance, then with 0 rotations, there should be 0 distance, 1 rotation, 2.5, 2 rotations, 5, and so on. That just makes sense. And that is linear, and so the equation would be the distance traveled is equal to 2.5 times the number of rotations. So, the students actually measured it instead of thinking about how that relationship is. Maybe they weren't clever enough to figure out that relationship, so they just wanted to measure. And this graph shows that measure, that relationship that the students got. And now notice that the points do go up, but they don't go up in a perfectly straight line. But we kind of know that it should be a linear relationship. So what can we do about that? Can we use the data they have to model the relationship even though it isn't quite perfect? And it turns out that we can. Now, one of the reasons that this data didn't turn out to be perfect is because of human error. When they're measuring, it's really hard to measure exactly distances. So there may have been some errors there. People weren't watching, they weren't recording the data as well as they should have, whatever. But we can see that this line does kind of go up there, and if you look closely, you might even notice that it's really close to 10 here at 4, which is about 2.5 revolutions. So what we're going to do is learn how to take that data and turn it into a linear equation if we think it's a linear relationship. And the line that you draw through the data to try and come up with your equation is called the line of best fit. So here's our situation. Breaths per minute and heartbeats per minute were measured for 16 people after they had walked for 20 minutes. The data are in this table. Now, as you know, the more breaths you are taking per minute, that means the more tired you are, or the more your heart is pumping blood. There's a relationship between the two. So the higher the breaths per minute, the higher the heartbeats per minute should be. Now these are actual data from people who did some walking for 20 minutes. And you could probably figure out also that the higher their heartbeat, probably the worse shape they're in this experiment. So here's the graph of all that data. And what we're going to do is we're going to try and draw a straight line that fits the points as well as possible. So you're going to take your straight edge, and you should do this as I do it. And the most important thing is that you get the same slope as the dots in the pattern. So try and make your line match the pattern of slope. And what I mean by that is, let's say let's get a bigger line here. Highlight it. If you were to look at these dots, you would see a pattern of dots that kind of looks like that. You want the slope of your line to pretty much match that grouping of dots. Okay? Then you want your line to go through the dots. And you would like it to split the dots down the middle, because we're kind of using the line to average the dots. So you would like to have about as many points above the dot as below, above the line as below the line. So I kind of like that line I have there. Now what you're going to do is you are going to try and come up with an equation to represent those dots. So we got our line, and B says write an equation of the line you drew. To do this, find the slope and the y-intercept of the line. So now you could estimate that slope and y-intercept. You could just use the graph. Make sure you notice the scale. But you can say, well, let's see. I can see it's about right here at 10:45. And let's see, where's another spot? And it's right about here at 30:90. So the rise is from 45 to 90 is 45. And the run is from 20 to 30, from 10 to 30 is 20. So I could do 45 divided by 20, which is 2.5. All right. That's one way to do it. I don't necessarily recommend that way because we were estimating a lot of things. I'm thinking to find the slope, it would be better if you actually found 2 points of data and used those. Like you might notice that mine hits this point right here. Put it in red so you can see it better. And it pretty much hits this last point also. So if I find the coordinates of those 2 points, so this one is about 16 on the x-axis, and then the last one, which is probably the last one in the data set, is about 44 on the x-axis. So 16 and 44 from my table. So that's this one and this one. Now, if I use those 2 points to find my slope, so 44, 120, and 1659. So I'm going to subtract my y values, that's slope. Subtract my y values and divide that by the difference between my x values. And that's equal to 61 divided by 28, and 61 divided by 28 is about 2.2. I think I can round it to 2.2 or 2.18, depending on how accurate I want to be. Let's say 2.1. There's my slope. Now that I have slope, I can find my y-intercept, and then I have an equation in slope-intercept form. Now my y-intercept I could estimate just by looking at the graph. There it is. And this is 15, that's 30, so I could guess that it's about 20 for my y-intercept. And about 20. If I wanted to get a little more accurate, I could actually use my values to find the y-intercept. Now, if you remember from the lessons, the y-intercept, we use the letter b for that quite often, is a y value minus the slope times an x value. So I could do y value, so I need to pick one of these y values, either 120 or 59. I'll do 120. And my slope I just found out is 2.18 times the x value that goes with 120 is 44. So I need to do 120 minus 2.18 times 44. So 120 minus 2.18 times 44. And there it is, 24.04. So I wasn't perfect with that one. 24 point, when I guessed by just looking at the spot right here. 24.08. All right, so I have my slope, I have my y-intercept, and I can now write my equation. Here it is. Y equal to my slope, which is 2.18 times x plus my y-intercept. Now what that means is this y-intercept value, just to remember here, that's 0 breaths per minute on the y-axis. So that means that when I am breathing 0 breaths per minute, my heart is beating at a rate of 24.08. So basically, you're barely breathing. And then my slope of 2.18, that means every time I take one breath, so my breath increases by 1, that means my heart beats go up by 2.18 beats per minute. So for every breath, your heartbeat increases by 2.18 breaths. All right, now that I have that, I can use that for some different things. Like, let's say I wanted to find an answer to something that wasn't in my data set. Like, let's say that I knew that somebody had 25 breaths per minute. We recorded 25 breaths per minute, and we wanted to know their heartbeat. Well, I could put my equation in my calculator, and I could do my slope is 2.18. That's 2.18 heartbeats per breath times 25 breaths plus my y-intercept, which I think was 24.08. And that gives me about 78.58. 78.58, and that seems to fit right in this data. So about 78 if there's 25 breaths. All right. And now, we did a lot of guesswork on that one. We kind of guessed where the line is. We used points that maybe didn't hit the line exactly. We may have guessed a little bit about the y-intercept. So one way we can improve the fit of our line is to make sure that we have the mean of the data in there. In other words, the average. So if we make sure that the average point is on our line, it'll improve the fit of our line a little bit. And that's what I'm going to show you how to do next. But I'm going to pause this video, and we'll have to do the second part.